Thank you. Thank you. Great. Thank you very much for the introduction, and of course for the shameless plug for my other life as a musician. I also want to thank the organizers for the invitation to come and talk to you today. It's going to be a little bit different than the preceding talks in the sense that I'm going to save the data for the end, in part because in trying to write a book that was primarily intended to convey to a popular audience the importance of soils and how humanity treats the land, how land use in effect sets the timescales that societies can thrive and prosper for, the essential argument in the book. It's something that is was a lot of fun to actually look into and look at. I'm going to try and give you sort of the brief overview of that today, and I'll make no apologies for the title of the book. My publisher assured me that a book titled Soil, the Stuff of Civilization, would not sell more than about 15 copies. Okay, and then I can probably advance this way. Yes. Well, those of you who are familiar with looking at the interaction of human societies and the environment and reading environmental histories have no doubt run into the argument and the idea that environmental influences and soil erosion resulting from deforestation in particular has been proposed as an idea to explain the demise of civilizations around the world. That whole set of societies over there on the right, from Mesopotamia, the Minoans, Greece, Rome, sort of Bronze Age Europe up through the Roman Empire, stuff in Asia, stuff in Mesoamerica, are places where people have made the argument. And as a geomorphologist who is trained, literally cut my geomorphological teeth out in the Oregon Coast Range, not all that many miles from where we're sitting today, the argument that deforestation per se could lead to the wholesale soil loss that has been implicated in the fates of many ancient societies and was something that just didn't really resonate very well with me, because we've been able to document that you do get a very large increase in soil erosion following forest clearing in the kind of environment that we're in here today. But it lasts a very brief time and occurs over a very small portion of the topography, in part because trees left to their own devices grow back and reforest fairly rapidly. And the idea that simply clearing trees as a one-off could actually lead to the wholesale loss of the soil just didn't really add up. So what actually might have been to blame? I started to look into the idea. First of all, one has to ask the question of, was extensive soil erosion associated with ancient societies, and did it have anything to do with their demise? This essentially forms the first half of the book. I'm going to give you a brief taste of that today, but of course it's a bit of a brief talk, and I want to get into showing you the data at the end, because the data was something into it. I wouldn't really actually try and reach the broad audience that I was hoping to get the message across to, because the bottom line message of the book and the talk are essentially that there is another long-term environmental crisis that's sort of brewing, and that is not about climate change or carbon sequestration, but simply about the maintenance of the soil and soil fertility. But it's essentially the next one over the horizon. The question I wanted to ask in this book, therefore, is could agricultural soil erosion limit the lifespan of civilizations? It seems like a fairly simple question to ask. I'm not going to advertise I'm the first person to have asked it. By no means am I. And nor am I the first person to really write a book based on soils and the relationship to civilization. It's in fact sort of my attempt to update a wonderful book called Topsoil and Civilization that was written in the 1950s. But since then, a lot has been learned about soil loss in ancient societies. Recent archaeological studies, as in the past several decades, have showed that soil erosion played a role in the demise of ancient civilizations in Neolithic Europe, classical Greece, Rome, the southern United States, Central America, in society after society around the world where one would care to look. I'm going to spare you most of the archaeological details of that today, but invite you to think about soil the way a geomorphologist like myself does. Think of it as a system that's produced and that's lost. I mean, for most of the scientists in this audience, that's going to be a fairly simple concept. Soils are produced from the breakdown of rocks, mixing with organic matter. They're stored on hillsides as the soil that's there, and they're lost through erosion. If you have almost any kind of a sloping surface to topography, soil will be moving downslope at some rate. The balance between soil production and soil erosion under a typical, whatever the climate, the vegetation, the topography, and geology one is in, will lead to the development of some kind of a typical soil profile. Soils are very diverse, very rich, amazing phenomena. I'm obviously not going to go into the detail of what those are today around the world. The key point that I want to make is perhaps the simplest point one can make about soils, and that is, over time, the change in soil thickness is going to be reflected as the net balance of the difference between soil production and soil loss. This may not be a terribly great revelation to anybody in this audience, but when you go out and talk to people in a general audience, most people do not think about soils as things that are produced and lost and changed. They don't think about topography as something that evolves over time, and it would be different if they were able to come back in 1,000 years and look at it. It's something that I've been trying to essentially convey to a general audience for the last few years with this argument. And how does this relate to the longevity of civilizations? Well, fundamentally, the invention of the plow fundamentally altered the balance between soil production and soil erosion. Why? Well, when you clear the land and expose it to wind and rain for some portion of the year, if it's not protected by vegetation for that time, you're commensurately increasing the rate of erosion. And if there's no commensurate increase in the breakdown of rock and the production of soil, then essentially you're losing soil faster than it's being made. And many studies, many of which I summarized in the book, have shown that conventional plow-based agriculture has increased soil erosion often by more than an order of magnitude. I'll show you the data behind that assertion later in the talk. But what I want to do first is give you a very brief introduction to the flavor of some of the kind of geoarchaeological data that one can put together to try and make this argument. Because obviously back in Neolithic Europe or Bronze Age Europe, or many ancient societies, there were not geomorphologists running around with buckets trying to collect sediment yield out in the real world. But if the coupled geoarchaeological studies that have been done in Greece, for example, have shown that cycles of erosion and soil formation began with the Bronze Age erosion event right after the introduction of plow-based agriculture. When the plow arrived from points east to the Greek landscape, there have been studies that have argued that the Greek landscape underwent a transition from open oak woodland, as Van Andel and Reynolds showed back in 1987, an open oak woodland in the immediate deglacial world that once the plow arrived, cultivation spread essentially right up through the hillsides. You can see this sort of thin layer of thin soil overlying on bedrock, and grain was cultivated up to essentially throughout the classical Greek landscape. And this resulted over time, they argued, in erosion of the soils and stripping of the upland environments down to relatively thin, relatively bare rocky slopes, and that much of the soil that had been up in the areas that were extensively cultivated in classical times is now found down on top of the original alluvium in the valley bottoms. And that there's areas where you can find agricultural implements on rocky slopes where you really couldn't grow wheat anymore. How did this potentially affect the population density in classical Greece? Again, Van Andels and Reynolds did something that I have seen very few archaeologists or geologists be brave enough to do, and that's attempt to reconstruct population density through time, going back from about 6,000 BC up to about the present in this region. And what they found is essentially sort of 3 cycles of population rise, first in the Bronze Age, a collapse in the vernacular some people throw at this kind of phenomena, or a shrinking of population density, a rise in the classical age of classical Greece, another low point in the southern Archelid, and then the modern age where the population rebounded. I don't think you have to think very hard to imagine explanations for the amplitude of those 3 different peaks. A bunch of guys with digging sticks in the Bronze Age are not going to be able to support the population density as people with fertilizers and John Deere tractors. Technology obviously plays a role. But what sets the periodicity? Why 3 cycles? Why an approximately 1,000 or 2,000 year kind of time scale between successive societies at this place? And indeed, if you look through the archaeological record, many societies last on the order of about 1,000 years or so, unless you're looking at floodplain-based agriculture where soils are replenished from erosion of upstream areas, and the arguments that are to follow in this talk simply don't apply. Other arguments apply there. Well, the problem of extensive erosion in classical Greece was noted by Plato. You could call him the first geomorphologist if you want some of the earliest literature that we have surviving in the Western world. And he essentially noticed the evidence for extensive Bronze Age erosion in the period of erosion before the classical age in Greece. And he wrote that the rich, soft soil has all run away, leaving the land nothing but skin and bone. But in those days, the damage had not taken place. The hills had high crests, the rocky plains of Phelus was covered with rich soil, and the mountains were covered by thick woods, of which there are some traces today. Now, not many people believed him until Van Andel and Reynolds started their work in Greece in the 1980s. Why? Well, he wrote this in his dialogue in which he discussed Atlantis, and it's not viewed among most scientists as sort of a terribly credible source. Yet he even estimated the time scale of the Bronze Age erosion event about right. He said that it had happened a couple thousand years before his own day. It makes for very interesting reading. Skipping all the other societies that I talk about in the book in the interest of time, I'll try and catch us up here a little bit, is that colonial North America essentially started as an agricultural colony, from investment bankers, if you will, in London. Their mandate was to return a profit on the people backing them to go to Jamestown. The thing that they actually figured out that would actually support them was tobacco. And tobacco growing, though, turned out to be a very a highly erosive crop. After about 100 years of tobacco growing, Hartwell Blaine and Chilton, in describing the present state of Virginia, wrote that so it is at present that tobacco swallows up all other things. Everything else is neglected, but by the time that the stumps are rotten, the ground is worn out, and having fresh land enough, they take but little care to recruit the old fields with dung. Essentially, soil management in North America in colonial days was tailored around optimizing tobacco cultivation, and you could only get about 3 to 5 years of crop out of, or high production out of land before it was extensively eroded because of the way that tobacco was cultivated and grown. It also exhausted soil fertility, but I'm not going to talk much about that today. I go into that in the book, but that would take even more time. But essentially, the whole phenomena of how tobacco growing influenced colonial society is a really interesting one. I'll skip the details today about how it set the stage for the rise of plantation agriculture, thereby setting the stage for the Civil War. But by George Washington's time, in the late 18th century, he was very concerned about the problem of extensive agricultural soil erosion in the colonies. He wrote that a few years more of increased sterility will drive the inhabitants of the Atlantic states westward for support, whereas if they were taught how to improve the old instead of going in pursuit of new and productive soils, they would make these acres, which now scarcely yield them anything, turn out beneficial to themselves. Washington was basically arguing that the extent of erosive degradation of colonial soils in North America would drive the United States westward, not because of some sense of manifest destiny, that came a century later, but simply because people were interested in the fresh soils on the other side of the Appalachians after having exhausted the soils along the eastern seaboard. To what extent did this happen, and how might this shed some light on the potential for soil erosion to have influenced ancient societies like classical Greece is shown by this map that, again, is not my work. It's based on the work of others, but it shows the extent of historical soil erosion in the Piedmont region of the southeastern United States, going from about Virginia to Alabama in this noodle here that is the Piedmont. It's not the Appalachians, it's not the coastal plain, but it's the upland hilly landscape where this kind of argument about progressive soil loss under cultivation applies fairly well. And you'll notice that something like 4 to 10 inches of soil had been lost through a couple hundred years of colonial agriculture in this region. Well, is this a big deal or a small deal? Well, when you think that the original topsoil thickness in this region has been estimated at having been about a foot, having lost a third to more than 2/3 of that in a couple hundred years, really puts in perspective what the Greeks could have done with a 1,000-year run at it, what the Romans did in central Italy, and et cetera in other societies. And I'd like to show this figure simply to make the point that, who in their right mind would think that you could sustainably plow a 45-degree hill slope? This is not something that could be sustained terribly long. You could imagine that soil erosion would be racing ahead of soil production in such an environment, and obviously I show it because it's an extreme example. The other example of soil erosion that could be viewed as fairly extreme is obviously the North American Dust Bowl. I'm not going to talk a lot about that today, but to share the quote from the first chief of the Soil Conservation Service, Hugh Bennett, who wrote in 1941, that I suspect when people along the seaboard of the eastern United States began to taste fresh soils from the plains 2,000 miles away, many of them realized for the first time that somewhere something had gone wrong with the land. The problem of soil erosion during the Dust Bowl, the problem of eating Nebraska's soils on your bagels in New York and in Boston, really brought the problem of soil erosion to the forefront of thinking in a mid-20th century American society, and it led to the development of the Soil Conservation Service. And just in case you might suspect that the establishment of a federal agency dedicated to soil conservation would solve the soil erosion problem in the United States, I want to disabuse you of that notion. This is a wheat field from about 40 years after the establishment of the Soil Conservation Service out in the Palouse in eastern Washington. And you'll notice all these small channels, what geomorphologists call rills, and it illustrates the fundamental problem with plow-based agriculture. At some time of the year, the crops are not going to be back in, and if you get rainfall on a erodible soil at a time of year where it's not covered, soil erosion can race ahead of soil production. The key question, though, is by how much? Well, this slide from the Palouse, from a 1961 paper by Vern Kaiser, shows that it can actually add up to quite a lot. This fence up here on the right is a fence around the farmer's cistern. The field was up at this level in 1911, at the level of the cistern, when the sod was broken for the first time, and it had only been plowed under conventional wheat production for 50 years, 1911 to 1961, and this cliff resulted as a result of the erosion from that agriculture. And this, which you can't see very well, but there's that little black thing there, it's actually a survey rod, shows up pretty well in the negative and some light, but that's a foot. So you have 5 feet of soil loss in 50 years. That's a foot a decade, that's an inch a year. There, as I'll show in a moment when I actually get into data, there is really nowhere on Earth that soils are forming about an inch a year unless you count places where volcanic soils are being added from above. At least, and Greg may be able to tell me otherwise, but what I actually did to try and, well, if you look back at the archaeological record, you can kind of triangulate the argument that there was a lot of soil loss associated with many ancient societies, but it's really hard to make the causal connection because the things were not sort of measured or observed that way. So one of the things that I wanted to do before trying to make the argument that agricultural soil erosion might indeed set a limiting timescale for the lifespan of civilizations, was to do that thing that has become, at least in my experience, incredibly hard to get at least undergraduates to do. And that is I went to the library, and I went there for 3 weeks, and I just got all the data I could possibly find on contemporary and long-term or geological erosion rates, and also on agricultural erosion rates in particular. Why did I look at geologic erosion rates? Well, if you think about that early assertion that in terms of soils coming into some kind of a balance with their local environment, the long-term rate of of geologic erosion, of rock erosion, is going to be approximated by the long-term rate of soil erosion, or there wouldn't be soil left in the landscape to begin with and go out and measure. They will be somewhere comparable. And this is what I found. Essentially 1,400 measurements of agricultural and geological erosion rates. It's a one-dimensional plot. Call it a UW plot if you want, but it makes it simple to actually think about. And the geologic data are shown in white. The agricultural data are shown in black. You'll notice several things. One, erosion rates are incredibly variable on this planet, down from rates comparable to Mars on the cratonal environments, the flat tectonically dead parts of continents. They go up to about 1 millimeter a year or so in steep soil-mantled terrain like the Oregon Coast Range behind where you're sitting. And I want to point several other things out. First of all, that alpine and glaciated terrain, things like the high Himalaya, the high Cascade, can erode at 1 millimeter or so or higher. And I want to, before talking about the agricultural data, I want to emphasize that in making this compilation, I did not use any sediment yield data. Why? I didn't want to get into the problems of things being produced in one area and stored in another. I'm trying to keep it relatively simple, and I did not use any model-based estimates of erosion rates. These are all actual field-measured data. Notice where the agricultural data plot here, that by agricultural data in this plot, what I mean is conventional plow-based agriculture, modern conventional agriculture, ranging from the third world to first world technology. A wide range. It also has, it spans 4 orders of magnitude or so, but you'll notice a couple things about it. First, that farms are eroding like alpine topography. Essentially, if you just look at the spread of the data from from plow-based agriculture, it's essentially at the very high end of the long-term geologic erosion rates. And in particular, if you sort of make the which of these things is most like the other kind of comparison, we've managed to turn the places that we farm globally, places like Nebraska, into places that are eroding at rates like the high Himalaya. It's actually quite a trick when you think about it. And the other thing I want to point out is this red bar here is the USDA soil loss tolerance values, which range from about 0.4 to 1 millimeter a year. Those are the range of soil erosion rates meant to define rates of sustainable soil loss. And I'd like to point out that they sit at the very far end of any kind of long-term data for any of the kind of places that we actually farm. Therefore, conventional agriculture as practiced in the modern world is unsustainable. That may sound fairly bold, but I think it's fairly simple and well defended. The next thing that I want to share with you in terms of data before trying to move on to the end here is that if you look at probability distributions for all the different kinds of data I was able to find in this several-week compilation, it's very instructive. What I've shown here in black are the 2 distributions that I just showed you previously. The geological data are the black line that runs through here. The conventional agriculture is the upper line. And it's a percentile plot, and erosion rate this time is on the y-axis. Those USDA sustainable or unsustainable values, as the case may be, are shown again in red. The new data I've added are all the data I could find on rates of soil production. There's been a closet industry in quantifying rates of soil production over the last 20 years, and we've been able to find, I was able to dig up a lot of numbers on that. Rates of erosion under native vegetation and rates of erosion under so-called conservation agriculture or so-called alternative agriculture, no-till agriculture and terraced agriculture. And the point that I want to draw your attention to is that I can't tell you that there's any difference between these distributions given the nature of this data, but the one thing that really stands out is the conventional plow-based agricultural data. Herein lies the good news as well as the bad news. The good news is that the problem is not, in terms of accelerated soil loss, is not that we farm. The problem is how we farm. Because conservation-based agriculture can reduce soil erosion rates to rates comparable to soil production rates. And in case you object to the idea of comparing these sort of broad distributions based on global data, which you should have concerns about, I want to show you the comparisons that I was able to find in the literature about places where you compare the human increase factor due to agricultural erosion. So if you take the ratio of the erosion rate that you would find under conventional agriculture to the ratio of erosion rate for the same soil, same climate, same geology, native vegetation, that ranges from about 10 up to 100. There's outliers on either end, but you get sort of a concentration in a box and whiskers plot. And if you look at the no-till decrease factor, the ratio of erosion rate under conventional agriculture to the ratio under no-till on the same kind of plots, the same slope and the same climate, the same kind of underlying geology, it decreases erosion rates by about the same amount. So no-till practices can reduce soil erosion by about as much as conventional plowing increases it. Therein, I think, lies the good news. If you don't like looking at distribution functions, this table simply summarizes the data I was able to find in this library compilation exercise. Both kinds of averages, medians and means, are shown over here on the right. Conventional agricultural erosion is on the order of somewhere north of 1 millimeter a year in terms of an average for the pushing 500 studies I was able to actually compile. And I'm not going to argue that I can tell any difference between these blue values for no-till agriculture, native vegetation, rates of soil production, and the very long-term geological erosion rates. They range from 1/10 to 100th of a millimeter a year. In other words, there's a big difference on the order, geologically, on the order of about 1 millimeter a year between rates of conventional plow-based agricultural soil erosion and long-term soil production. I'm not the first person to argue that rates of global geologic erosion are on the order of, a couple % of a millimeter a year. There's a few other studies. Bruce Wilkinson's work in particular is quite good. And rates of global soil production estimates are, sort of comparable on the order of, something less than 10% of a millimeter a year. Right in line with what I was able to compile. There's one other study to share with you, in part because I think it is so clever. Bruce Wilkinson did a study where he looked at trying to reconstruct geologic erosion rates over all of geologic time, or at least the last 500 million years of geologic time, by looking at the distribution of sedimentary rocks in the geologic record. What he found is that for the last 500 million years, the average erosion rate in the continents is about an inch every 1,400 years. This compares to the average rate of soil erosion off of agricultural lands at present of an inch every 60 years or so. So essentially which itself is about 10 times shorter than the USDA's estimate of rates of global soil production. So virtually any way you cut it, whether from looking at modern studies looking at rates of soil loss to looking at soil loss over most of geologic time, or at least since land plants evolved, our agricultural soils are eroding at something like 10 to 20%, 10 to 20 times, any kind of conceivable replacement rate. You can put together a very simple model for estimating the time required to lose a soil of a thickness S as a function of the difference between the erosion rate and soil production P. It turns out to be a log linear plot like many simple analytic models. But if you basically take the idea that on average we're losing something like a millimeter a year of soil as the net difference between erosion and production rates, and recall that's conservative according to the data that I compiled, and you basically look at what that would mean for the loss of a half meter thick or meter thick soil, these two lines here, you essentially go up to here, take it over here, and you're talking 500 to 1,500 years or so as the predicted time scale for agricultural soil erosion, the way it's been practiced around the world for millennia, to exhaust the soil physically. And we're not talking about soil fertility in this case, we're actually talking about conserving the soil itself. And that timescale reasonably approximates the time spans of most major civilizations. Can we quibble with this in detail? Absolutely. And can I basically rule out things like climate or natural disasters? No. In terms of their influence on the longevity of human societies? No, and I'm not trying to. The argument I'm trying to make is that this long-term slow bleed of soil may be what is setting the long wavelength periodicity behind the rise and fall of human societies. I don't think soil erosion actually terminally ended any society. It happens too slowly to actually do that. But in terms of setting the sort of the health and potential of societies, I think it actually is sort of the big underappreciated influence that has been acting throughout history. I'm also not the first person to argue this, and I'll end here by quoting Walter Loudermilk, who wrote that here in a nutshell, so to speak, 50 years ago, we have the underlying hazard of civilization. For by clearing and cultivating sloping lands, and most of our lands are more or less sloping, we expose soils to accelerated erosion by water or by wind, and in doing this we enter upon a regime of self-destructive agriculture. It's a lesson that I think is as pertinent today as we talk about how to actually think about the potential role of biofuels, say, in our long-term energy solutions, because if we actually embrace conventional farming practices to produce unconventional fuels, all we've done is perhaps delayed by a few decades and changed the crisis that we'd be facing. And in the interest of time, I think I will cut it off there. Thank you for your attention. I did bring copies of the book if anybody's interested in getting one, and naturally I encourage you to come and check the band out tonight, and I'll shut up now. Thank you for your attention.
So we have time for some questions.
Very interesting. You suggest that in order to preserve the soils, we need to change farming practices. In the current world, I don't know how much of the food supply is by industrial farming, but I'd assume a large fraction. So, is it possible to supply the global population with enough food by changing the industrialized farming practices to practices that do not erode the soil?
Thank you. That's an excellent question, and I'm really glad you asked it, because that's something that when I started doing the research for the book, I would not have been able to answer. And it is a concern that I think is sort of the first one to think about. What I've been really impressed by is how many studies there have been now over the last 10 years in particular, looking at crop yields under no-till versus conventional agriculture, and they're pretty comparable. On some kinds of terrain, on some kinds of soils, one is higher than the other. Now, the key thing with no-till is that it's not necessarily incompatible with large-scale industrialization. In fact, one of the critiques of it is that it often is associated with increased pesticide and herbicide use. And you could think of sort of organic agriculture and no-till as parallel tracks. In the book, I argue we need to get both those together and figure out how to do organic agriculture in a no-till fashion over the long run. But of course, the other potential answer to your question is if you look at where the highest crop yields on the planet are, they're not in large-scale industrial farms. They're in very small-scale, labor-intensive organic things. Some of them are actually in cities, urban agriculture. So in terms of how we would actually be able to feed the planet using so-called alternative agriculture, I think that it's perfectly feasible to do so. Whether we would actually be able to do the political and economic transitions that it would take to enable that to happen is a much bigger question in my mind now than whether it's simply feasible to do. And organic agriculture can yield the comparable crop yields to conventional as well. So there's just different ways to do it.
One more question?
Thanks for the insight in your book. You talked about ancient societies which lasted on average 1,000 years. So they lost their soil. Right. It's a rule of thumb. But where do we stand today in, say, recent societies? Have we already gone, towards the end of that 1,000-year lifespan that we have? Or are we just missing evidence of societal collapse during the last 2,000 years?
I think that if you look around the globe, there's a real big differences in where we would sit with that. Where we're standing today, the native forest here was cleared a little over a century ago. So we're just starting. If you look at the Middle East, they've played through. And so I think the real message behind recognizing this as a phenomena that has affected regional societies in the past is not to get locked into the same practices globally for the next 100 or 200 years, because we don't really have anywhere else to go. And if you look at the places where you could argue that you could find a lot of new agricultural land, the Amazon basin or the Tibetan Plateau if you could get water to it, there's things that we could do that probably wouldn't be sustainable. In terms of the Amazon, at least we might be able to get, with conventional agriculture, at least we get a decade of productivity out of it at best. And in India might complain if China took the Tsangpo River and used it to irrigate the Tibetan Plateau. So I think the key point is really not so much that we face an immediate crisis or that any one particular place is at really high immediate risk, but that if we look globally and if we look through climate change, because clearly I think that's the much more immediate and pressing problem. We'll have to deal with the soil problem. But if you look at the problem of how we would actually sustain agricultural production in a post-petroleum world when nitrogen-based fertilizers might not be the optimal way to maintain soil fertility, simply from economic considerations, we ought to be thinking about alternatives, and the idea of being able to park more carbon back in the soil, which is a side benefit of no-till agriculture, is something that ought to be kind of thought about in terms of dealing with climate change, because that would help with the next crisis that is admittedly a bit farther off.